Okay, thanks, Ricardo. Good morning or good afternoon, everyone. The next course of today is about one of the most fascinating aspects of quantum field theory in curvature spacetime, which is the fact that different observers may not agree on what a vacuum is. And to guide us through this topic, it is my pleasure to introduce Professor Bruno Arderucio Costa. Bruno is currently an assistant professor of physics at the Center for Relativity and Cosmology at Troy University in the United States. And he completed his PhD at the University of British Columbia under the supervision of Professor William Unruh, one of the most of the pioneers of quantum field theory in curvature spacetime, which is also the main focus of Bruno's research. Bruno also has extensive teaching experience at both the undergraduate and graduate levels, including courses in general physics, quantum mechanics, and advanced general relativity. I believe this is a great opportunity for anyone interested in quantum field theory in curvature spacetime to learn from an expert in the field. So I encourage you all to make the most of his presence. And also, since this is an online session, I think it is better if only the Bruno, in this case, who is speaking, keep their microphone on. And if you have questions, you can write in the chat or raise your hand. Without further ado, Bruno, the floor is yours.
Thank you, Clara, for the kind introduction. Yes, I might not be monitoring the chat so closely, but if you leave something, you can feel free to unmute yourself at any moment. I want to start with a motivation before anything else, which surely, if you've taken any course in quantum mechanics, you've certainly seen the commutation relation between position and momentum as QP I H bar times the identity. And that's no mystery to anyone. And what we normally do, we decide to make Q act on a function while these are acting on L2 of R, for example. And when we get the action of Q on a function as the product, QFQ, that's what we do. That's position operator in most of the times. And then we take P acting as minus IH bar d by dq. So I'm sure all of you have seen this many times. Now you may ask, why? Why do we do the way we do? Well, we could, why not? So why not? This is what we all do, but why not acting on the same L2 of R? Well, you see, we can take P as a direct multiplication. And we could take Q as IH bar d by dp. I claim that this satisfies this commutation relation as just as this choice satisfies this commutation relation. And you can see that directly. You can directly apply IH bar d by dp on P times F.
Sorry, Bruno?
Yeah.
I think here the people say that the board seems to be blurry. I don't know.
Oh, is that a focus problem? Thank you for interrupting. Is it out of focus or is it too small?
I think his focus, maybe you can make a zoom and then.
Well, that's unfortunate. I've tried this before and it usually worked. Let me see if I can.
Too small.
Well, if it's too small, that's an easier fix. I might just write a little bigger. So if I write this size, does that work? Is that more legible?
Yeah, it's better. It's better.
Yeah. Okay. Thank you. So all right, bigger with the downside of not being able to fit as much on the board, but that's good to go. So yeah, so that's what we're trying to verify, that I h bar d by dp of the product pf minus p times I h bar d by dp of f. Well, you can use the product rule, and this is easy to see that this is I h bar times f. So this is that. This is the commutation relation that we had before. So fine. So you may even have seen this before. It's actually used in quantum mechanics, and this is no mystery. You don't expect this to be causing a clash of physics. Physics is not broken because you have this different choices of how you want to represent these operators on L2 of R. In fact, you know exactly why they are the same. We are talking about, you can think of that as these two choices are connected by a Fourier transform. And in fact, that's how, in the early days of quantum mechanics, that's how these things were developed in the first place. We had de Broglie relations, etc. And this is a way of implementing them. Of course, we grew up and we decided that this is the most important relation. And after we did that, we are seemingly faced with these two different choices. But this is pretty inconsequential, right? So let's see another example. Let's consider now not of L2 of R, but little L2 of Z. So if you've heard of polymer quantization, this is the thing. I'll have to erase because of font size. So I wanted to consider, so again, this is the base is now labeled by integers. So I wanted to consider this Q acting on N as a e to the minus I H N N, and P acting on N as a shift N plus. Well, let's evaluate QP on N. This I minus IH bar, N plus 1, N plus 1, and which is e to the minus IH bar, PQ on N. Okay, so that's the commutation relation. You might not be, well, if you attended the previous course, you might already recognize this, but if not, let's see what happens if we have, you see that if we have QP, little q, little p, IH bar, and then we consider Q because the exponentiated version of that, so capital Q is going to be IQ and capital P e to the IP. And let's see what happens to the commutation relations for these exponentiated versions if I fix the commutator for the non-exponentiated version. Well, we can apply Baker-Campbell's-Hausdorff. This commutator is a multiple of the identity. So once you apply Baker-Campbell-Hausdorff, you just need to carry about the first commutator. All other commutators are going to be proportional to the identity, and they're going to be 0. So that's easy. So so QP will be the exponential of I, little q, little p, minus the commutator divided by 2, which is just h bar divided by 2 in this case. And same, sorry, for PQ. With a different sign. So comparing these two, QP on N is e to the IH PQ on N. So there should be a minus sign. So that's where they come from. So these implements, so I'm getting a little bit ahead of myself. So this is related to the Weyl algebra that we're going to talk about shortly. But you see that this, you can see of this, you can think of these operators as implementing, again, the commutation relations that we wanted in the beginning. But now, is this the same physics? Well, I haven't defined yet what I mean by being the same physics, but I think you can already tell that it cannot be the same physics because this is discrete. So there must be a different physics content in this version as opposed to the previous two. So that's what this mini course is all about. It will work as we're going to learn to, well, first of all, we're going to make it precise what I mean by same physics. That's the first step. The second step, we're going to characterize what kind of freedom we have in choosing, given a certain algebra, how we represent it, what is a representation of our algebra, and the physics content in the representation of algebra. And it will also work as an introduction to algebraic quantum field theory. What this course is not about is writing, stating theorems and going through the proofs in detail. That's not what we're going to be doing. For that, there are a few reasons for that. One of them is that the proofs are not always simple. The second reason is, well, they are in the references. Some will require a fair bit of function analysis and more advanced topics. But also, the primary goal of this course is taking you who've seen quantum mechanics I'm sure you all did. And even if you study quantum field theory in curved spacetimes in a more conventional framework, such as in Biro and Davis' book, after this mini course, you'll be able to understand the language and import your intuition that you already have to this more algebraic framework. So that's the plan. Are there any questions at this point? And again, if you have questions, you are free to unmute yourself. If you prefer to write in the chat, maybe someone can help me if I miss the message, so we can go smoothly. Okay. So yeah, we're gonna leave this aside. We're gonna come back to this example shortly, but I wanted to start with is more review of some topics that we're going to be using throughout the course. Perhaps I think the easiest beginning is start what I mean by an algebra. Well, if you again, there's a bit of an overlap with the previous mini course. So you can see an algebra as a vector space, and you have an extra operation, which is the product operation, and you have some, it's associative and so on. We are talking about algebras that contain the identity, an element, and that multiplies and gives you back the same element you multiplied with an inverse, and a star operation, which functions like taking the Hermitian adjoint of matrices. So one star is one, the identity. Sum of the stars is the star of the sum, and the product's the same, but with the reverse order. And a representation is making that these algebras act on a Hilbert space. So they become concrete. So if you just have rules of operation, now you have actual objects, you can know what they are and more concretely. We are going to see this as more tangible through examples, just like these ones. But I wanted to start with a small review of symplectic spaces in classical mechanics, because that's how we are going to talk about Weyl algebras, etc. So we're going to talk about a pair as sigma. It's going to be a symplectic space or a phase space in classical mechanics. So we require sigma. So sigma S is our space, and sigma is a non-degenerate antisymmetric form. So in classical mechanics, and in general, this is always true when you have the structure of a cotangent bundle, if you're seeing differential geometry. But if you have, just thinking about a particle in classical mechanics, this sigma can be dp wedge dq. And you see, even if you're seeing in any of these differential geometry, this is, you can see why we need this to be antisymmetric and non-degenerate when you write equations of motion in the Hamilton form, like p dot related to derivatives of an Hamiltonian function and so on. So yeah, so I said, the example that we have to keep in mind, that's the leading example, is sigma dp wedge dq. So the Poisson bracket, and you see concretely why this is the way it is. If you look at the Poisson brackets between two functions, and you see that this can be written as this form acting on the derivatives in phase space. These are phase space derivatives of f and g. So the minus sign in the Poisson bracket comes from the antisymmetry of this sigma function. If you have a Poisson bracket, you can use the Dirac quantization procedure, and the Dirac quantization procedure will take qi qj equals pi pj. These are 0, and qi pj is ih bar delta. So we can unify them using this symplectic form as sigma of y. So y now is an element of the. So this is a collection of p and q. So this is in phase space. Q is configuration space. P is associated the conjugate momentum associated with that coordinate. So this unifies this as yj equals minus I sigma. Well, we're going to set h bar equals 1 for the rest of the meaning force. So these are the canonical commutation relations. Now, we're going to do what we did before in that example. We're going to take the exponentials of that. And you may ask why. One reason, the lazy way to get out of this question of why is to mention that you take exponentials and they convert unbounded operators to bounded operators. In this case, that's one way of seeing, but this is not the full answer. And in fact, the version with the exponent, so the Weyl versions, which is similar to the capital P and capital Q I had in the example before, there's a stronger condition in this condition. And well, if we have time, we can mention a little bit of that. But anyway, so from the canonical commutation relations, let's define W y as the exponential of that. So this, you can think of that as, yeah, you see, this is mapping. You pick an element of the space, of the phase space, and this gives you another one. So, yeah, and then the Guidures, we repeat what we did in that example, the little L2 example that I had before. So it's the same idea. We have the commutator relation here, and it's also proportional to the identity, so it's easy to apply Bacon-Campbell's-Hauser. And if these operators satisfy that, the CCR for two of these becomes this. Watch for sign conventions. Different references will sometimes use different sign conventions. But these are called the Weyl relations. So you can think of that as, well, together with the star of y. So this is, so this, again, this is, you think of that as a way of imposing the canonical commutation relations, but in fact, it's a little strong. Well, the reason why I'm mentioning this is that we can now answer the question that I posed in the motivation. When do we know? When can we know if? Now I'm given this as the fundamental entity. I need to find. So this is the algebra that we are looking for. Now, if I choose different representations of the algebra, am I going to get different physics? And the answer to that, it's, well, if that was the whole story, this wouldn't be a mini course. But we're going to start by talking about a theorem, which I'm not going to prove, which is called Stone-von Neumann theorem. And it will provide an answer for, in our cases, which are, well, under its hypothesis, of course. And we're going to see what they mean. And it's also going to give us a clear definition of what I mean, different physics. Well, maybe let's start with that. What do I mean when I say different physics? You see, what you measure is expectation, well, it's matrix elements. So given a Hilbert space and an algebra, and a different Hilbert space and an algebra, what I actually measure, according to the postulates of quantum mechanics, are matrix elements. So if I reshuffle the elements of the space and I shuffle, so if I act, or maybe there's more room. So this is, well, what I'm trying to define is unitarily equivalent. So given an Hilbert space and an algebra, and I'm giving two of them, I say that these are unitarily equivalent if there is, well, let me not write as many words because I don't have much room on the board, but these two are unitarily equivalent if there is a unitary U from H to H prime, such that if I take U to the -1, A prime U, that's A for all A prime. A prime. So this way, so if I transform the elements by acting U on them, or U -1, and I transform the operators by this kind of similarity transformation, then the matrix elements that I get are always the same. If the matrix elements is the same, when I'm going to make predictions in my quantum theory, the predictions are going to be the same. So I have the same physics. Is that clear? Is that do you all agree that's a good criterion for calling preserving the physics? Good. Very good. So that's so the Sloan von Neumann theorem is going to say something about when this unitary equivalence happens. One of the hypotheses of the Sloan von Neumann theorem is continuity, specifically something called strong operator topology, which strongly continues. It's strong and continues in the strong operator topology. One way of characterizing, so we need to talk about the space of operators, so the linear maps from H to H itself, and we need to define a topology in it. There is more than one topology that you can place in that space, but the one that we're going to use for this theorem is it's called the strong operator topology, and you can take as a basis of that. So let me perhaps write as a basis around the origin of that. Yeah, we're not going to be proving this theorem, so we're not going to go into too much of that. But I suspect you've already seen this in the previous mini course if you're attending it. So you will get a basis. Well, we can even write as S around your S and L of X and Y. So these are operators that come from L. They're mapping X to Y, such that the norm of S of Xi is well, that's the Y norm of it. It's smaller than epsilon for a finite collection of I and a positive epsilon. And the nice property about the strong operator topology is that the convergence happens if you have a sequence of T operators goes to 0 for all x's in X. Well, anyway, don't get intimidated by that, because we're going to see an example in which well, maybe let me not say this yet. But anyway, with that, we are ready to write to state Sloan von Neumann theorem. So let me just use that. Well, let me see if I can fit it down here. And there is another very important hypothesis, which is the focus of our attention. Which is, well, let's take S and sigma as a symplectic vector space, but 2n dimensional. So finite dimensional. This is critical. And the reason why you're having this mini course in the first place. So if you get a 2n dimensional symplectic vector space, so the statement is this: any two strongly continuous irreducible unitary representations of the Vacua relations are unitary equivalent. Well, I hope you're convinced of the importance of talking about unitary representations, because we're doing quantum mechanics, and in quantum mechanics, we want preserved probabilities. So the way of doing that is think of unitary transformations and we want the maps basis. Suitable. And okay, irreducible representations, well, that means that you can't decompose it into direct sums. And this is an obvious way of, if you want to find a finite dimensional counterexample of that, all you have to do is to take direct sums, and there we go. You don't have unitary equivalence anymore, so that's boring. Even though there is significance, you can interpret that. This mini course is all about looking at examples and understanding what they do. We can talk about that. So let's not look into let's not take that. So let's look at the irreducible representation zone. So in finite dimensional, so in fact, that's the reason why we don't talk about, if you're taking regular quantum mechanics courses, we normally don't talk too much about the choice of representations, and that's the reason. Because if they're all equivalent, unitarily equivalent, and then you are given the same physics, and you can really focus on the algebra instead of focusing on where your states live. In the language of quantum mechanics. And instead, you focus on the algebra itself. Now, in quantum field theory, this is going to be violated. And it's really not possible to generalize that. And you're faced with the need of specifying representations as well as algebras. So before we continue, there's just one observation that I wanted to establish, is that for matrices, if there is this A, so that's just a side remark that we're going to use shortly. It's a one-line calculation. Let's say that if A and B are related by a transformation of this type, what happens to traces? Well, using the product, this is a one-line calculation, so maybe let me write it. U, B, U, dagger, B, U, using the properties of daggers and reversing the orders, and using that U is unitary, the traces of dagger times itself are preserved. Okay. So now let's go back to the example that we had before. After all, I was intuitively trying to argue that the second example in my motivation, the one that had discrete basis elements, and P, capital P, was a translation on that. It's a kind of a lattice quantization. In that case, I was trying to convince you, based on your intuition, that had to be different physics. In the language of Stolfer-Neumann theorem, something must have gotten wrong with it. What is it? It's certainly finite dimensional, but you violate strong continuity, and you can verify that by just realize that P of n minus n and look at the norm of that. So if n is normalized, this goes to n plus 1. So this thing is root 2. So you want, so P to the power to the certain parameter won't do the job. But now what we're really interested in, so we're going to apply that and re-verify what the condition of unitarily equivalence. So let's characterize unitarily equivalence. And now we're going to leap into quantum field theory. And if, well, it doesn't have to be quantum field theory, but it's generalizable to quantum field theory. We'll talk about squeeze states, if you heard of them, and decide when you have two unitary equivalent representations there. So if you're seeing anything about quantum field theory in Kerr spacetimes, again, in most traditional expositions, you must have heard about Bogoliubov transformations. And so let's review them, and let's see, let's apply that to what we are discussing. And let's pay attention to an aspect that's, if you're reading Parker's book, for example, you may not realize the importance of one of these conditions. So let's talk about that. So this is just a quick review of Bogoliubov transformations. So let's say we have, I assume most of you have seen this before, but let's assume that we have this sort of CCRs in terms of AA and daggers now. So this is just delta AK, and we have a combination. Is this still legible? I hope so. All for AK plus beta AK. Now, of course, we're going to impose that this tilde combinations of A and that. So these are those coefficients, Bogoliubov coefficients you've seen. So we are taking a combination of them, and we impose that the CCRs also apply to tilde operators. So A tilde I, A tilde K, delta IK, dagger. And let's also write this in matrix notation. It's just more convenient to do so. So what we find proposing this, well, let's not do the calculations. It's you can do it, or you can see in virtually any books. But in matrix notation, there's alpha dagger. This dagger not to be confused with this dagger. This is just the dagger in the I and K's indexes. So yeah, not this. Just don't get confused by the notation. Minus beta dagger. That's going to be the identity matrices. And so that comes from this equation, but we also have to impose the decommutator between tildes without the daggers. So to A commute every time. So in matrix notation, that will read as alpha beta transpose minus beta alpha transpose is 0. So these two. So you have these two sets of A and A daggers, modes, etc. Well, yeah, that's the minimum that we need to continue the discussion. Now we can talk about its vacuum state in the usual sense, in the sense that if we have A of I, so we can define two states. So we can define a state AI that is annihilated by all AIs. Then we can define another state annihilated by all AI tildes. And we want to relate these two states. Well, surely we should be able, I'm sorry. Surely we should be able to relate those states because we have a relationship between these aces and daggers. So if you have one mode, there is a way that you you can do that kind of elegantly and without putting any ansatz. Well, anyway, let's not talk about that. Let's use as ansatz to see how this guy looks in terms of this mode. So what we can do, we can put it as ansatz. Um, 1 divided by the capital Z of the exponential of 1/2. So this is gonna, well, I'm gonna suppress the sum notations because this is, and you may imagine why I'm taking the pair of these two. So in the language of particles in quantum mechanics, well, you were creating particles in pairs because you have two, and then, well, you're not gonna write a Taylor series for this exponential. You're gonna always have even powers of a different modes, and you have this matrix make ik mixing them. Okay, so now we pose, so let's put the ansatz in this equation and see what we get. Yeah, I'm really gonna try not to write too many long calculations, but well, this one is might be instructive. So AI tilde 0 is, I'm suppressing indexes now. JL. Now what you can do, chances are, well, if you haven't seen this, every time you see a commutation relation like this, what you can do, you can apply that, you can verify, well, what I'm going to use is this equation, and I'll come in 1 second for it. AI and a function of AJ dagger. That is the same as taking the derivative in respect to AJ dagger of AJ. Well, if you haven't seen this before, you can convince yourself that this is good. How do you do it? Well, first of all, you write this for a polynomial. You suppose that this is a polynomial, and you can use you write it, prove it by induction. Well, just take a power. Take a power of f as a power of this guy. Just a simple power. Prove by induction that this works. Then you can prove that this is true for polynomials because you can multiply the scalars and etc. And then you use density to say that this is true. So if it's true for all polynomials, you use density arguments to verify this in general. So this is, you can verify that if you haven't seen before. So this works when you have this commutation relation. So now if you apply this to this equation here, so you wanna put these all A's acting, well, this is, you know this from the harmonic oscillator of quantum mechanics. You wanna act all these A's to the right, and you move to the right using this commutation relation here, and you get the following. You get offer ik exponential anyway. So, well, let me skip some. Let's not bore you with all the calculations. Let me skip a few lines. So you get two terms. One term there is, so you get alpha m, so you get alpha I k m m k k dagger plus beta I k k dagger times the exponential acting on 0 times the exponential acting on the vacuum being 0. Now you use linear independence, and you to conclude that alpha ik mk plus beta ik equals 0 for all ik. Or in matrix form, it is convenient. This is the product of matrix. Here I'm using the matrix. So this works if this matrix is symmetric, but it is. And I know the matrix is symmetric because of the form of my ansatz here. And these two commute. So I can happily call this the matrix multiplication between my alpha Bogoliubov coefficients and this mixing matrix. Plus beta is 0. So I can, and again, because of the Bogoliubov relations, I can invert this alpha. Alpha has to be invertible, beta doesn't. Alpha has to be invertible. Otherwise, the transformation is singular and you're reducing the dimensions, so this doesn't work. So m is alpha to the -1 beta.
Bruno,
Okay.
someone
Yeah.
is asking, what are the indices of the last m?
This equation.
Yes, I think the before, the indices.
I can read the indexes. So sorry, let me. I k m k I k. I am sorry if this is too small. Try to write bigger and even bigger now.
Okay, it's okay
But
now.
yeah, it is. Yeah. Does that clarify?
Yes, perfect.
All right. So this gives you them. You still need to find this normalization constant z, which you will. Well, at least maybe at least tell you how to do it. Maybe let me not do it because if we don't want to spend our valuable time together just writing long expressions and simplifying them. But this is very important. Well, this tells you many things. For example, if beta is 0, well, this is expected if you've seen Bogoliubov transformations before. But if beta is 0, this m is 0. And this tilde does nothing for you, right? Because this is a 1. So that's the first observation. But in general, and then again, and then there's a lot to talk about here. For example, you see that this m is mixing different modes, so it's a very natural question to ponder when m is diagonal, because then you're creating particles of the same kind, the same mode. If you're talking about, or when it can be diagonalizable, anyway. So we can talk a lot about that. But our emphasis here is slightly different. As you can imagine, we are talking about unitary equivalence. So having a non-zero beta is not telling you that it's okay. It's just saying that it is related by that. So let's see what happens. Let's have a look at the normalization constant. To look at the normalization constant, we need to impose that linear product. So okay, let me erase something. So we're going to impose that tilde is the same as until n. So that will, using this ansatz again, we know who m is, but using this ansatz, we have square negative of z as the expectation value of this exponential 1/2. I'm going to use matrix notation here. A transpose m dagger a exponential 1/2 of a dagger transpose m a dagger acting on 0. And now, well, now I have to open this. If you use, you can think of that as weak theorem. There's one way of doing it. Let me say how I try to do it. That's my favorite way. If you have your favorite, feel free to use your favorite way. This is just one way of continuing this calculation. That's not the only way, but I like to open this exponentials as series, and 2 to the 2n, one for each exponential, n factorial squared. And then you get a bunch of m complex conjugates, I1, I2, and then you get a bunch of these products of these m's, K1, K2, acting on 0, AI, a I1, a K1, again, like that. And now, again, what you really do need to do is to commute everything. And similarly to how we did in the identity array raised using derivatives, you can take a series of commutators like a dagger to the power p. You can write this as d by d a dagger and a power p derivative of a dagger to the power p, which is just p factorial. Okay, well, and again, so using that, so that's one way of doing it. Using that, you get, let me write here in the bottom. So you get that z is some infinity n factorial divided by 2 to the 2n n factorial trace of m dagger m to the power n. So the upshot is that this can only work when the trace of m dagger m is finite. That's the condition that we're talking about. Well, we can even rewrite, we know who m is, so we can rewrite this condition as trace of beta dagger alpha to the -1 dagger alpha to the -1 beta. Now we can write this as this guy as alpha dagger to the -1. Why? Well, you can check that. So I need more room. So why did I say that? Well, you can verify it immediately. Alpha dagger alpha -1 times alpha dagger to the -1 to the -1. So this is alpha -1 dagger, alpha -1 alpha dagger, which is just identity. So this is indeed the inverse of that. So this is just to show that this guy is the inverse. So yeah, this is the justification of this step. But using this is which is 1 plus beta dagger to the -1. So this tells you that trace of beta dagger beta is finite. So this is a condition we're after. And this is a condition that you can easily overlook if you're just interested in talking about, if you've seen some expeditions of the Arrow effect or even Hawking radiation and whatnot, or squeeze states. This is squeeze states, even if you're looking at optics. And anyway, so you may have seen this many times, but this is the, it's kind of shifting the attention to making this finite now. This is the condition of unitary equivalence. And this has an interpretation in terms of particles as well. You may have seen this before. And the way you've seen that is to talk about a number operator. If you have an interpretation of particle, this has this very simple interpretation in terms of the number operator. Perhaps let's write that real quickly. We are not going to be talking about particles very often in this course, but this is a situation in which we do have a clear interpretation in terms of particles. So if I look at the number operator, tilde number operator, and we write the Bogoliubov, you write this, well, there's a tilde, and we write this 8 tildes in terms of the a's. This is, well, I shouldn't write too many details. This is an A. I'm sorry before starting to write too small. Now I want to move all these A's annihilating these guys, and this A daggers annihilating the guy on the left. And this is so in the language, so this is sum is implicit here. So this is the total number, the expectation value of the total number of the tilde particles in the untilde vacuum. So this condition is saying that the number of particles is finite, if you want to have that interpretation. And in the identity that I showed later, if this betas are related by a unitary transformation, u beta u minus 1, this condition is, this is the same condition because of the identity that we discussed later. Okay. Let's see, there's an action. The Arrow effect is probably the first example that you see using all these Bogoliubov transformations. So let me use, probably this is going to be the rest of what this is probably about all I can use my time today to talk about. But let's review the Arrow effect and let's see what happens in this condition for that example. Yeah, let's do that. So, okay, I'll erase this. If you have any questions, that's a good point. While I erase this. Okay, so let's briefly use the Unreal example. Well, write bigger. So the Unreal fact, we can start by writing. I'm using the notation of Unreal's original paper. So on the right is d rho d toy squared minus 1 over rho d rho squared minus dx squared minus dy squared. So rho is positive and yeah, so positive rho. So now you may say, well, what is this? And if you've seen this before, you're going to find this a bit tedious, but I'm not going to give you too many detail. It's 2 root of, so this coordinate transformation, and you can promptly identify what this coordination transformation is. So this coordinate transformation brings this line element to dt squared minus z squared minus z squared. So this is the usual line element, and if you have this, you can think of this trajectory and you see what happens if you are in a particle in which tau is the proper time. And these coordinates, you can promptly realize that you are a uniformly accelerated observer. Well, for them, the coordinate tau will measure the proper time if you are in that position. So now we're going to solve the wave equation. Well, the wave equation, I should say the Klein-Gordon equation. So we all know that these modes for a given k and a given omega. Well, let me label it further. Well, let me use not capital phi, so to avoid problems. So a given omega and a given k, separation constants. You look at exponentials. Into the minus I k x. Well, this solves the massive Klein-Gordon equation if omega is, so if omega, well, this solves box minus mu squared x, phi 0 if omega is square root of k squared plus mu squared. Now this is, you can see from this line element, but we can also see what happens if we write Klein-Gordon, this box operator in terms of these coordinates, and we solve in terms of that. And you can see that, well, let's do that. So what you can do, you can, well, first of all, we're talking about, let's label. These coordinates don't cover the whole Minkowski space. Instead, they cover just a quarter of it. So this is what we call R plus. So for magnitude of, for Z larger than magnitude of T, that's what this covers. And then R minus, this is the future, and this is the past. So we are looking at the modes there in this area. And there's a causal, well, there's a lot to discuss here. In, if you have a benefit of the hindsight, well, there's a lot to discuss, but let me state that you can choose modes with their R plus to refer to this area. Omega tilde, because these are different sets of modes, we're going to apply a Buber-Huber transformation between them. So I minus I omega tilde times tau now on root of, and well, you may also wonder why this normalization constant is doing. I'll get to that in a second. 2 pi cubed, and I'm writing too small again, so let me start writing bigger again. G of rho e to the minus I k perp x perp. X perp is just a collection for x and y and not z. So this will solve the equation. So now we can see what the differential equation for rho, G of rho, is after we write that. So let me not derive that, but the equation is, okay, perhaps I should write the equation. Well, so the equation is rho d by d rho of rho d by d rho of g plus omega tilde squared g minus mu squared plus k squared rho g. Now rho only covers the wedge, so we are going to have to write, if you're going to write a full phi, this won't work because this only covers, this coordinate system only covers the right wedge. But what we can do, we can write a second set of coordinates with a minus in front to denote that this covers with that, with the reflection. And then if a general field expression will have to be some of k perp and omega tildes, but with a restriction, if this is positive, we're going to talk a lot about this restriction. Not today, but starting tomorrow, we're going to talk a lot about this restriction, what this is doing. And in fact, we're going to see that this is a way of characterizing your representations. Well, we're going to talk a lot about that, but this ensures that the Klein-Gordon product is positive definite for these modes. So we have to have a set of modes in R plus and another set with A minus. Well, plus Hermitian club. So we need 4 terms then. Now the trick to evaluate these Mogolyovich coefficients, which is the trick that Arro introduced 50 years ago, is to analytically continue this across the boundary. And specifically, the trick is that if the Klein-Gordon product, we know the Klein-Gordon product is preserved across different surfaces, then if it's preserved across different surfaces, I can evaluate the Klein-Gordon product on a surface, on a characteristic surface, in particular in a null surface. And in a null surface, the normal derivative points in the direction of the surface itself. So I can, just by knowing the value of the fields on the surface, I will know its derivative as well. And I can, yeah, it simplifies everything. So, yeah, let me talk about how you do this trick of analytic continuation. So first we are going to, well, so this is the surface in which you're going to evaluate everything. So this is the surface rho equals 0, which is t equals minus z. And here tau goes to minus infinity in this surface, because you have to move it this way. Now you define capital coordinates. Yeah, I'm sorry, I don't have much room. So if you write capital U is t minus z, capital V is t plus z, U equals tau minus log of rho, and little v is tau plus log of rho. So on R plus, so we can relate these coordinates, and U becomes plus or minus. I'm going to explain what this, well, minus a plus. I think I'm going to explain what this means in a second. 2 e to the minus u divided by 2. This is, if you, well, this is the near horizon approximation. So this is, this is kind of the surface. Well, anyway, let me not. 2 e to the v divided by 2. So the top sign is for r plus, and the lower sign, the bottom sign is for r minus. Now what do you do? Now we're going to look at the equation for g as rho goes to 0. And the way to do that is using a power series. All right, so the way you do it, you write g of rho is rho to the s, a naught plus a1 rho plus etc. Then you take the derivatives, and then you take two derivatives. Well, let me spare you of all these calculations, and you get the integral equation, and you see how this behaves, and you see how this solution behaves as rho goes to 0. All right, so yeah, you've probably seen this Frobenius method before for approximating solutions. Let me skip that. It's already, we are kind of in our time more than I thought we were going to be at by this stage. So you look at the lowest possible coefficient, and well, a naught is going to be different 0. So you verify that equation. So s must be 0. Well, there's a double root. But anyway. So then you look at the coefficient of rho. Well, the next coefficient, you get a solution for a1. So anyway, so let me write what you get after you substitute. You take the derivatives and substitute that, and collect the same powers. You get s equals 0, and you get a1 plus omega tilde squared a0 equals 0, which gives you a1 equals minus a0 omega squared. And so g of rho or the whole rho squared. And now you restrict the modes that I had written before in terms of the right movers evaluated at up to order rho. So you have a term independent of rho plus order of rho. And then you do the same for the left movers. And then when you restructure. Anyway, let me try to skip these calculations. Well, again, if I'm skipping this, but that's quite of generic. If I'm skipping these calculations here, you can look at the original paper. It's one of our references, and I'm also going to be skipping proofs and other arguments. You can always refer to the original derivations. And I often think that if for a mini course of this format, it's more useful to focus on examples that build intuitions and the ideas than it is on following the calculations or sometimes even the proofs, because you can do that. It's not. I'm not saying that this is easy, but especially if you're here for next week for the event that's happening next week. We need some sort of shortcuts, and that's we are humans having a conversation. I find this to be more useful for this sort of format. So yeah, all of that is to say, I hope you forgive me for skipping many of the arguments. But you can write in these coordinates. The realization is that this mode is positive normed. Okay, I'll have to erase something. So this Minkowski mode you can write this as omega plus kz capital U divided by 2 e to the minus I k perp x perp or root of 2 pi cubed omega at v equals 0. Now, this has positive norm, and the reason is that omega positive implies omega plus kz positive. Why? Because omega is the square root of k perp plus mu squared plus kz. So even if kz is negative, this has to be larger in magnitude than kz. So this is omega is, well, that's because omega is magnitude more larger than the magnitude of kz. And yeah, so now you build the modes. Yeah, let me not write them because they are a little big, but the key is that you build a positive norm mode in Minkowski mode and a positive norm in R plus for U positive and U negative, and you can continue them. And when you continue them, you pick different factors. And that's the celebrated factors that give rise to the Unruh effect. So what I'm going to write is just this expression that you have to verify in the end. The e to the pi omega tilde R plus lambda. Lambda is just a collection of all the separation constants plus e to the minus pi omega tilde AR minus of lambda dagger acting on the Minkowski vacuum in 0. Okay, so once you get to this expression, this is exactly the form that we were discussing in the generic framework of Bogoliubov transformations. So we can write the new state, and the new state is going to be, so the Minkowski state is 1 over that normalization constant times that exponential. Well, but that's product of lambdas of exponential of e to minus 2 pi omega. Now, oh gosh, I'm sorry about writing this way, but lambda plus a r minus lambda dagger acting on the tilde. That is the Unruh effect. Okay, there's a lot of points that I was focusing on getting this expression, but now let me discuss a few points that I left before. Well, first of all, the interpretation of this. If you've seen the Unruh effect before, I'm sure you've seen this interpretation. So this looks like, well, first of all, again, creation of pairs, and this creation of pairs are in the same mode. So like this M is diagonal with the difference that this creates a particle on the right and a particle on the left. They're created in pairs. And if you trace out the left side, and that's what Unruh did. So you trace out this left side, so you're left with this exponential term, and you get now a mixed state, thermal state, kind of a Gibbs form. And he works it, of course, if this guy is well behaved, as we discussed before. So that's the original argument. And so after you trace out, you get a thermal state because of this exponential factor here. And of course, this is fixed by acceleration. If you have any acceleration, you have to rescale tau, so that's the proper time, and you repeat the argument, you get Tolman-like temperatures and etc. It's we could talk a lot about that, but the points that we want to emphasize is this is instantiation of this the Bogoliubov transformation the way we wrote just before. Now there are many details that I should probably clarify a little bit. First of all, the normalization, the reason, the need for taking positive omegas. So first of all, what is the product? What is the normalization? The normalization we are talking about is the Klein-Gordon product. What is the Klein-Gordon product? Well, it's the symplectic product. It's the symplectic product that we introduced in the beginning. So if you have a Lagrangian, you can find the associate momentum to that. The associate momentum will give you a symplectic form, the same way that you had for classical for the one particle. So this gives rise to a product. That product is just, well, it's just a product. To have a quantum theory, you need to have a Hilbert space. To have a Hilbert space, you need to have an inner product. And I'm not saying that the Klein-Gordon product that you get from the symplectic product is an inner product. Well, okay, maybe let me write, just be a little bit more concrete. What is the Klein-Gordon product? U and V, it's going to be I integral. So we are in the Minkowski space to T of V. It reacts. So this is Minkowski space. So U, the T derivative of V minus V T derivative of U bar. So this is the Klein-Gordon product. So this is just I times the symplectic product we had before. This T derivative, so obviously we're going to generalize that to, well, so if you're in a generic globally hyperbolic space-time, you need to talk about how you can write again on a Cauchy slice, you can write a Lagrangian, and you identify conjugate momentum as you normally do. So this is, it's as you can guess, the generalization becomes U nabla V, this sigma A. So that's root of A, the induced metric, D3, well, which is Riemannian, because it's, if this is a time-like surface, the induced metric is Riemannian. Sorry, it's a space-like surface, and the induced metric is Riemannian, and then it's and that's just what the inner product becomes. Antisymmetrized, because that had to be antisymmetric. So that's how we are normalizing these modes. That's why we pick this factor here. And we only pick this omega positive. And the reason we pick that as omega positive means that you can verify very clearly for the modes that I raised, when you have just exponential modes in Minkowski coordinates, this product is just 2 times omega. For the same omega, if you plate the same phi omega twice here, this inner product is just 2 times omega. So this product is positive. The norm, if you want to say, of omega is positive only if and only if omega is positive. And that's relevant because one candidate for a Hilbert space, if you want to talk about a quantum theory, will be the subset of all your complex solutions. So let's look at what you're doing. You have the equation that I erased, which is the Klein-Gordon equation. Then we are considering complex solutions of that equation to describe a real field. Then you may search among those solutions, the ones that have positive norm. This object will satisfy the other axioms of an inner product. And with that axiom, well, maybe that's an inner product. Maybe that's what we're going to do. That's a Hilbert space. And we can build a quantum theory of that. And once you have a Hilbert space, a one particle Hilbert space, well, we know how to talk about particles. We know how to talk about Fock spaces. Now you have a quantum field in which the space of states is a Fock space, which is a symmetrized, so Fock space on a H is C direct sum with H, direct sum with the H tensor H, symmetrized, because it's both on the field, and so on and so forth. So it's a state that has a vacuum part, a one particle part, two particle part. But if we frame of our discussion, there seems to be a lot to characterize about that. Can we talk about different one particle Hilbert spaces that live in the same Fock space, so to speak? In fact, that's what we're going to see starting tomorrow. And we're going to see that this is really motivates the study of a algebraic framework of quantum field theory. I guess I could, yeah, I'd rather not. But, I could enunciate the axioms of, well, let me maybe discuss, the idea of we're going to jump and make a, we're going to abstract away a little bit. And why are we abstracting away, you may ask? And, I think the answer is clear, especially when you are talking about quantum field theory in curved spacetimes, because as we're going to see, we want to talk about states that you can't reach by applying this Daggers operators sometimes, and there might be physics relevant for all of them. So what we're going to do starting tomorrow, I'm going to lay down some axioms of algebraic quantum field theory, and we're going to characterize the freedom that we have in the choice of one particle Hilbert spaces, and we're going to see why we need to make this leap of abstraction, so we can talk about all sorts of states, even in absence of that. Yeah, let me take questions now before, and we'll stop here. But let me take questions first.